ask me questions, and I'll try to be more careful with definitions and notation, but also want to ask others if you have any questions, and maybe you were afraid to ask those questions in the first part of the talk. So it's a good time to ask any questions you had about the first part now. Yeah.
No, it's just the screen went blank.
Oh yeah. Okay, it's a good question. Yeah, it's blank here. Okay. Yeah.
Could you tell me how this integer program can be solved in practice? I mean, how efficiently, like for how many variables we can expect to get an optimal solution?
I see. Yeah, I probably can't really tell you this. I mean, yeah, I don't have that much experience working with integer programs, but for many problems you can. If you use the right tools, something like Simplex or Gurobi, they're quite powerful. But
of variables or billions or just thousands?
It really depends on specific integer programs. So for some integer programs you can do more, and for some others you can do less. And then there are many kind of practical tweaks you can do, like introducing various cutting hyperplanes for the LP. And of course, some powerful toolkits like Simplex, Gurobi, others, they already have very good, so they know how to generate good cutting hyperplanes and various other techniques, but you can also tweak them manually. So depending on that, depending on how well you formulate a linear program. So for some problems, you can do this, and maybe this is sort of the first choice you want to do. So if you want to solve a optimization problem in practice, of course, the best way is to first try maybe some combinatorial algorithms, like maybe local search, which works very well in practice in many cases, but not always. And maybe the second choice afterwards is to formulate your problem as an integer program and try if it works, because then you're done. And if not, then you need to do something more sophisticated. Okay, so now we have, again, our problem, the same problem, minimum set cover. And we have now, we have this linear program for it. So as I said, if you look only at integral solutions that require every x sub s to be either 0 and 1, we'll get a solution, and the cost of the solution we denoted by IP, integer program. And we know that the cost of the integral program exactly equal to the cost of the optimal solution to the original set cover problem. Now, once we replace x sub s to be a variable taking values from 0 to 1, a continuous variable, we no longer have that property. So the optimal cost to the linear program can decrease. So we know that it's less than equal to the cost of the integer program, just because any valid solution to the integral problem is also a solution to our linear program, but we can get potentially more fractional solutions to the linear program. Fractional meaning that the variables are no longer 0 and 1. So how to, but the good thing about this linear program, and the reason why we write it, is that we can easily solve it using either Simplex algorithm or interior point method, or if we talk about theory, the ellipsoid method. Let's see how to convert the solution to LP solution to some approximate solution to the original problem. So we want to sort of convert this LP to some solution. And what we will do, we'll do the following. So we'll write the following algorithm. First, we'll solve the linear program. And this can be done, again, quickly and in polynomial time. And then for each set S, in our family, let's pick it in the solution with probability proportional to the value of the corresponding variable x sub s. And let's pick it to be 2 log n times x sub s. So of course, this probability, this quantity can be greater than 1 as well. So if this quantity is greater than 1 or 1, then we'll pick as this probability 1. And that's it. So this is the algorithm. We solve the LP, we get this variables x sub s, and then let's say maybe x star sub s is the optimal solution to the linear program, and we output solutions like this. So let's see. So we need to check 2 things: that the algorithm outputs a feasible solution to our original problem, that's a set solution to the set cover problem, and we need to estimate the cost of this solution. So let's try to do these 2 things. And maybe we'll start with estimating the cost. So what is the cost of the solution returned by the algorithm? So I'll denote by alg the cost of the solution. And now the algorithm is really randomized. So it depends on some randomness. So it makes sense only to talk about estimated cost. So E is an expectation. So in Rush, I guess I would write M for math expectations, but expected cost of the algorithm over the randomness we have. And this is just, we can sum up. This is equal to sum over all sets S. And we count it as 1 if S is chosen by the algorithm, and 0 if S is not chosen. And of course, this is the same as sum over all sets S in our family. And we're just looking at the probability that S is chosen by the algorithm. So what's the probability that S is chosen? It's just 2 log n times x star S. In fact, it can sometimes be less. So if this number, summation over all S. So for some sets, it's 2 log n times x star sub S. For some other sets, this probability is less if this quantity 2 log n x star S is greater than 1. So we have an inequality here. So we rewrite it as 2 log n summation of x star S. And this is just equal to the value of our linear program, right? So this was our objective value of the linear program. This is the quantity we wanted to minimize to begin with. So that's the cost of the LP. So we get it's 2 log n times LP. And as I said previously, the cost of the linear program, of course, is at most the cost of the integral solution. And the cost of the integral solution is exactly equal to the cost of the optimal solution to the original problem. So we get, again sort of log n approximation. The only thing so far, we don't know that this is a real solution. So we know that the cost of this family is 2 log n times the optimal value, but we need to verify that it is a solution.
So up to this moment, it is not actually essential for us that the date is 2 log n.
Right. So far, it's looked pretty arbitrary why it's 2 log n. So we'll see why 2 log n is important. Maybe we got a hint that it needs to be something like log n from our previous combinatorial argument, but let's see why it really works. And so to argue that this is a solution, we need to show that every element in our domain is covered with very high probability, right? So only if all vertices are covered, this is a solution. So let's look at one vertex. So let's fix some vertex v in the domain. And let's see what's the probability that v maybe is not covered, doesn't belong to this union. I have some notations here. Let's denote, so I'll denote by f2 prime the family output by the algorithm. So what's the probability that S doesn't belong to the set of covered vertices? And it doesn't belong to the set. If it doesn't belong, so we can see it. It shouldn't belong to it means that if you look at any set S containing I, that S shouldn't be chosen by the algorithm. So so it means that it's essentially the same probability that for every S in our family, such that this set S contains our element V, S is not chosen, right? And in the algorithm, I maybe didn't mention it, we do all these choices independently. So the probability that S is not chosen for one set is 1 minus two log n times x star S. And again, here is a small caveat. Of course, this number can be less than zero. So if it is negative, think of it just as 0. Because if one of these coefficients, x star sub S, is greater than 1 over 2 log n, we will pick that set S with probability 1 to our solution, which means that that element is always covered. So if for some v we have at least one x star sub S, which is sufficiently large, larger than roughly 1 over log n, then because this quantity 2 log n times x star S is greater than 1, we will pick S in our solution with probability exactly 1. But otherwise, so this probability that the vertex V is not covered by any set S is equal to the product over sets in our family of 1 minus 2 log n x star sub s. And this probability is less than, so we use just Poisson approximation. We can replace this 1 minus 2 log n x star s to e to the power of minus 2 log n x star s, and rewrite it as exponent of minus sum of maybe minus 2 log n sum, sorry, here s only, sorry, we look, of course, only at sets S that contain our vertex, fixed vertex V. A summation of x star sub s. Okay. Any questions? And now, because x star sub s is the solution to our linear program, we have that the sum is greater than or equal to 1. So this was our original constraint, right? So we have this constraint that if you sum over all sets S in our family F, and we look at those sets covering one specific element, in this case it was I, then this sum is greater than 1. And of course, any solution to the LP must satisfy this constraint. So we have that the summation is greater than or equal to 1. So this exponent is less than or equal to e to the power of minus 2 log n, which is 1 over n squared. And we are now almost done. So for every vertex individually, we have this bound that probability that that vertex is not covered is less than 1 over n squared. And now we use the union bound, and we have that the probability that there exists some vertex v such that v is not covered. It's less than the number of vertices in our domain, which is n times this probability 1 over n squared, which is 1 over n. So we get a valid solution to our problem with probability very close to 1. Okay, so this is a rounding technique. So in practice, often we want a solution, an algorithm that always outputs a good solution, a valid solution, but we rather want just the cost of that solution to be in expectation good. So of course we can tweak this algorithm slightly to produce a feasible solution all the time. We can, for example, modify our algorithm and so do the same steps as before. But if there are some uncovered vertices, which happens with probability 1 over n, we will add the following step. So we will cover every uncovered, yet uncovered, covered U with just some set. Some set and arbitrary set. In this case, we'll get that the cost of the we obviously always we will get a a feasible solution because we'll cover all the elements, but the cost will slightly increase because we have this step, but the number of extra sets in the expectation is very small. So in this case, it is at most the optimal value over n squared, right? Because every vertex can be covered by one set, and one set has value at most the cost of the optimal solution, and we add that one set to every vertex with probability 1 over n squared. So in this case, we'll get 2 log n times opt. So the algorithm value is at most 2 log n times opt plus opt over n squared. So this is again sort of order of log n approximation. And this algorithm.
So could you explain again why the second sum?
Here it's probably here, like n. Here, sorry. Yeah, I'll do it in a second. Here, so if you now suppose we run this algorithm, so with very small probability, it returns infeasible solution, right? So not all vertices are covered. Then we can take for every vertex just one set, arbitrary set, and add it to the solution. So the cost of that set, okay, so in this case it's just 1, but it's less than the cost of the optimal solution, since the optimal solution has cost also at least 1. And so for every vertex, the probability that it is uncovered is 1 over n squared from the previous computation, right? And then we have n vertices. So in expectation, we will add, so for every vertex, opt over, at most opt over n squared, and we have n vertices. So in expectation, we will add at most n times opt over n squared, which is opt over n. Okay?
So it's expectation.
It's expectation, yeah. Yeah.
So right here we can reduce factor 2 times log n to 1 plus epsilon log n.
Yeah.
So
Hmm?
because here we can just reduce to 1 plus epsilon times log n and get just less probability, maybe more time to work, but better solution.
Yeah. Yeah, so 2 is not optimal here, but
Can we reduce less than log n factor?
no, that's not
There
possible.
is no rounded technique.
No, the log n is the best, and there is matching hardness for this problem. So this is one of those maybe few problems for which we do know the exact hardness of the problem. So it's not possible to do better than log n. It's an NP-hard problem.
What assumptions?
I believe that this is just p is not equal to p. And sort of this LP algorithm, one good thing about it, it also can work with weighted instances of the problem. So if our sets have different weights, and our goal is to find not the minimum number of sets, but a family of sets with minimum weight, then the same algorithm will work. And it's really easy to see because we'll just have in the previous analysis at certain places just we'll have to add the weights of those sets. But since the algorithm is so simple here, essentially the cost of the solution really is computed here. Hmm?
Does the previous greedy algorithm work for weighted?
Yes, actually it also does work here, the same. But here it's even more straightforward to see it. Okay, so let me now. So how much time do I have? Okay, yeah, so, and then again, any questions, no matter if you don't understand some definitions or some notation or anything at all, please ask.
What's the point? I mean, we have a greedy algorithm, and this one is 2 log n. The previous one was simply log n.
Right, just different techniques. Because sometimes these techniques are more useful. I wanted to illustrate on something. This algorithm can also made to be log n. I didn't want to go into details. It's a little simpler to have 2 log n.
Can we randomize it somehow?
Yeah, we can here if you care about randomness. For me, randomness is pretty much free, right? It's, you know, if you run on a modern PC, as far as I'm concerned, randomness is free for us. But yeah, there are various techniques to de-randomize. You can probably, yeah, so there is this technique of conditional expectations. So essentially, every time, instead of picking a random set, you can compute the expectation over kind of the remainder of the set. So you instead of picking a set S with certain probability, you see what happens if you add that set and if you don't add the set. And what does it mean? You see what happens. You can compute the cost of this solution using sort of this algorithm. So computing the cost, this is easier, right? It's just 2 log n times the optimal value. So it's just 2 log n times the LP value of the remainder of the set. So you kind of, there are ways, but whatever. And very standard ways, but. And maybe now let's switch to another interesting question and another problem, which is, I'll talk about balanced cut and sparsest cut. And I did talk about this topic a week ago at some other seminar in Moscow. And maybe some of you attended that seminar, but today I'll talk about this problem in a very different context. So I'll give different proofs. So even if you've seen it a week ago, this may be interesting to you. So what are these problems? So I'll talk about balanced cut, sparsest cut, and most importantly, about embeddings of metric spaces. And this is, I think, a very fascinating area of research now. That also has various practical applications. So the balanced cut problem is the following. Suppose we have a graph G. And let's say we have it on 2 n vertices. And our goal is to partition our graph into 2 pieces, left piece and right piece, so as to minimize the number of edges crossing the cut. So we want to minimize the number of edges going from L to R, right? So the goal is to partition the vertices of this graph G into L and R. L and R are disjoint sets. And we want to minimize the number of edges going from one piece to another. And this problem is very natural, and it has many extensions that, again, I used in theory and practice. So particularly if you think maybe as various divide and conquer algorithms, they always want to partition your graph into several pieces and then work with every piece independently. Also, if you want to partition your graph in many pieces, then maybe this can be used directly as a black box. So kind of sub-procedure, you partition your graph in 2 pieces, and every piece again in 2 pieces, etc. Also, many techniques that used for this problem can be directly used for other graph partitioning pieces, graph partitioning problems, and especially now when there are various problems in big data. We have huge social networks, maybe like Facebook. We often want to partition data maybe in the Facebook graph into many pieces to allocate them to different servers and stuff like that. And usually we want to reduce the number of connections between various pieces or parts of the graph. So what's known about this balanced cut algorithm, balanced cut problem? So maybe I'll first give you some summary of results. And the first polylogarithmic algorithm was given by Layton and Rao in '89. So they gave log n algorithm for the problem. And then later, Linear London and Rabinovich, and independently Oman and Rabbani in 1905 sort of also gave log n algorithm, but okay, maybe for slightly more general problem. And they pointed out to the connection between this problem and metric embeddings. So essentially what they showed that if you use a classical result by Bourgain about embeddings of metric spaces, so this result of Bourgain is from '86, then we can also get log n approximation. So the result of Bourgain is really about metric embeddings. And this is the algorithm I will talk about today. So in this algorithm are for this. So the algorithm of Bourgain is for metric embeddings, and then the algorithm of this algorithm we originally developed for this sparsest cut problem. But it is very closely related to the balanced cut problem. I want to point out that these results find not really log n approximation by what's called by criteria log n approximation. So they find two sets L and R that are of size approximately n, approximately half of all vertices. They can be a little bit off. But however, they compare their cost to the optimal solution to the original problem. If we want a true approximation, then there is a result of Rake from 2008 that gives true approximation log n for this problem. And finally, let me mention that Aurora, Rao, and Vazirani in 2004 gave a square root log n approximation for by criteria version of the balanced cut problem. And this is using semi-definite programming. So I will talk about semi-definite programming sort of in one of future days, but maybe not about this algorithm though. And all these new results, meaning the result of RV also uses metric embeddings. So metric embeddings are very powerful techniques nowadays in constructing various graph partitioning algorithms. So this is a balanced cut problem, and a closely related problem to it is the sparsest cut problem. So what is the sparsest cut problem? We again given a graph G, but now we don't necessarily want to partition it into equal pieces, but we want to cut away some piece from it, some set S, such that the set S has a sparse boundary. So the number of edges crossing the boundary between S and its complement is small comparing to the size of the set S. So in other words, we want to find the set S, subset of all vertices, let's say that contains less than half of all vertices. And minimize the number of edges going from S to the complement, the number of edges crossing the boundary, divided by the size of the set S. And so sort of how to solve this problem? Again, we will write a linear program relaxation for the problem. So suppose we have some solution, S star. In fact, just suppose we have some set S star. So define an integer program corresponding to this define some variables corresponding to this set S star. So S star is some just feasible solution to our problem. And let's do the following. So this partitioning of the set of the graph G into two pieces, S star and the complement of S star defines a metric on the vertices of the graph G. So what is the metric? So the metric is defined as following. So I'll denote it by x because later we will use this distance in our linear program. So the distance between two vertices x, between two vertices u and v, let's say that it is equal to 1 if u and v are in different pieces according to this cut S star complement of S star. So 1 if either u belongs to S star and v belongs to the complement, or the other way around, if v belongs to the S star and u belongs to S star complement. And let's say that this distance is 0 if u belongs to either S star and v belongs to S star, or maybe both of them belong to the complement. Okay? So this defines a metric, and I'll tell you why in a moment, between on the set of vertices of the graph G. So it's easy to see that, first of all, of course, this function x of u and v is symmetric because x of uv is equal to x of vu. So technically, it is a semi-metric because the distance from one vertex to another can be equal to 0, even though these vertices are distinct, are not the same. So it's sort of a relaxation of this notion of metric. And what the main property we need to check that this function satisfies the triangle inequality. So let's look at some 3 vertices uv and w, and the triangle inequality tells us that the distance from u to v plus the distance from v to w is greater than or equal to the distance from u to w, and we need to verify this condition, and it is clearly satisfied because so if u and w lie in the same part, either in S star or in the complement, then x u w equals to 0. And since all the distances here are non-negative, the triangle inequality obviously is satisfied, right? So the right-hand side equals to 0, and the left-hand side is non-negative. Now, if u and w lie in different pieces, then x u w is equal to 1, but v must lie either in the same part as u or in the same part as w. So one of the terms, either xuv or xvw, must be equal to 1, and the inequality is satisfied as well. And such metrics, in general, are called cut metrics. So this is a cut metric. So, right. metrics corresponding to cuts. Now, so instead of finding the best sparsest cut, we are going to look at the best cut metric. And we will rewrite the constraint of the sparsest cut in terms of the cut metric. Yep. So sorry, I just can't hear you.
Can you state more clearly what should be the respective volumes of vectors parts of this graph?
S and S complement, right?
Yes. For example, if you have S as an empty graph, what should it be? Is it stated in the terms of rho, or it should be a variable to approximation?
Right. So the question was, what is the requirement for the size of the set S? So in this balanced cut problem, the sizes of both sets should be approximately the same. Formally, we really want to find maybe some constant such that in this case, this set both L and R contain some, maybe not half of all vertices, but constant a fraction of all vertices for some constant. C is some universal constant. Think of it maybe 10%. Or in the sparsest cut problem, this set S can have arbitrary size. Okay, it can be empty. Then, yeah, sort of the problem doesn't make any sense. It should contain less than half of all vertices. And that's just sort of S and the complement are symmetric. So this requirement is not really essential. We could as well just replace S here by the minimum of size of S and the size of S complement. So it doesn't really matter. But it's easier to state the problem in these terms. So essentially, there are only two conditions on the set S. It should contain at most half of all vertices, and it should be empty, because then the problem is not really defined. Okay, so let's try to rewrite this problem in terms of cut metric. So what is the size of the cut? So first, we want to rewrite this summation. We want to rewrite the number of edges going from S to S complement in terms of the corresponding cut metric. How to do that? So we will sum over all edges in our graph. And we will count 0 if this edge is not cut, and 1 if the edge is cut. And so what does it mean? And we exactly have sort of indicator variables for this event. These are distances between U and V, right? So if U and V belong to different pieces of the cut, then XUV is equal to 1. This is exactly what we want. So this is summation over all edges in E XUV. Now, to express the other term, it's actually a little bit more challenging. So we have this term S, right? Let's instead look at the product of S and S complement. And note that this product is approximately equal, 2 minutes. Okay, yeah, this product is approximately equal to n times the size of S. Why? Because S complement is a bigger size. So it contains somewhere between n over 2 and n vertices. And again, if we talk about approximation algorithms, then the approximation in the end we get is log n. So we don't really care about maybe two factor in here. So we can, in our objective, replace S with S times S complement divided by n. So what we get is that the size of S is approximately equal to S times S complement over n, up to a factor of 2. And this is good enough for us. Okay, and now to express S times S complement, it is easy. This is the number of pairs separated by the cut. So the number of U and V such that U lies in S and V lies in S complement. So, and this expression is very similar to the expression we had before, so to this expression. We just need to sum up UVs not over all pairs, but rather, not over all vertices, over all edges, but rather over all pairs of vertices. So, and this is XUV. All right? So we get 1 in this summation if U and V belong to different parts and 0 otherwise. And the number of U and V's that belong to different parts is obviously exactly equal to S times S complement. We can pick U exactly in S different ways and V in S complement different ways. And sort of this is almost the LP program we have. So essentially what we are going to do, we'll try to find the cut metric. And we have expressions for our objective function. So far, we don't know how to sort of divide the number of edges going to S to the complement by the other expression. But this is what we are going to do next time. And
there's a factor of 1/2.
Yeah, there is a factor of 1/2, right? That's why it's approximate equality here. But OK, so we'll deal with these problems next time. And I think this lecture is over. Do you have any questions? OK, thank you.